Okay, so in this lecture, we're gonna continue the previous topic, which is CPU scheduling. So in today's lecture, we're gonna cover the rest few classic CPU scheduling policies, including round robin, priority-based scheduling, multi-level feedback queue, which is a comprehensive version that tries to combine the best of both worlds of shortest job first and round robin, and finally lottery scheduling. So in the meanwhile, the CPU scheduling worksheet has been posted on Blackboard. So before diving into the detail of today's topic, in the next couple of slides, we'll be first briefly going over what has been discussed in our last lecture, while at the same time answering those practices in the CPU scheduling worksheet. Okay. So let's first do a brief review about the first two basic scheduling policies: FIFO, first in first out, SJF, shortest job first. Okay. So, we'll be starting. The most fundamental basic scheduling algorithms are based on as I've mentioned in the previous lecture, based on some unrealistic workload assumptions. So here we look at these four specific workload assumptions. The first one, the job runs for exactly the same amount of time, right? Which is obviously unrealistic. And the second assumption is, all jobs are arriving on the system at exactly the same time, right? And then the third assumption is all jobs are only featuring CPU burst, but not IO burst. And then the fourth assumption is the runtime of each and every job is known ahead of time. And as we go, we will, cross over each and every one of these four assumptions, and we eventually reach to a point where we basically remove all these assumptions, and we're really looking at the problem with relatively realistic assumptions. This is when we talk about the second to the last scheduling policy, which is multi-level feedback queue. Okay. So in our lecture, we first talk about FIFO, first in, first out, right? So its core idea is pretty straightforward, right? Operating system just go ahead, schedule the jobs based on their arrival timestamp, basically based on the arrival order, right? So here we first look at this performance metric, which is the waiting time. And the definition of waiting time is defined as the timestamp, the time when the process first gets scheduled by the operating system, the start timestamp, subtracting its arrival timestamp, the time when this process first arrives at the system. And here in this example, we're looking at three different processes: P1, P2, and P3. And recall that we use these examples are based on those four mentioned assumptions, right? So all these different processes arrive exactly the same time, but in subtly different arrival order, which is P1 arrives before, slightly earlier than P2, then P3. And here, the bottom half of the slide, it shows the Gantt chart for the CPU, the job schedule. So P1 finish first, and then P2 followed by P3. If you want to calculate the waiting time for P1 is 0. For P2 is essentially the the span of P1, right? Because P2 needs to wait until P1 gets finished, which is, 5 time units. And then P3 needs to wait until both P1 and P2 gets finished. So the waiting time of P3 is 10. So we just sum all these three time spans together, which gives you 15 and 15. In order to calculate the average waiting time, you just do 15 divided by 3. Gives you 5. Okay? And the next interested performance metric that we've also kind of discussed in our previous lecture was this turnaround time. So according to its definition, turnaround time is the completion timestamp minus its arrival timestamp. So if we still take a look at exactly the same example where we have these three different processes, right? And each of these three processes, they feature exactly the same burst time, length, duration. But even though they arrive exactly the same time, they follow like a particular order. P1 arrives earlier than P2, earlier than P3. If you want to calculate the turnaround time, so the turnaround time for P1 is 5, and the turnaround time for P2 is the whole span when it initially arrives at the system all the way to the point when it gets finished, which is 10, right? Which is 10. And the turnaround time for P3 is the same. Similarly, you calculate the turnaround time for P3, the finishing timestamp, which is 15, subtracting its arrival timestamp, which is 0, gives you 15, right? So the average turnaround time for this system is 5 plus 10 plus 15 divided by 3 gives you 30, divided by 3 gives you 10, okay? So this is average turnaround time for this particular example. So let's revisit all these workload assumptions. So recall that the very first assumption is each job runs for exactly the same amount of time. So this is the very first unrealistic assumption that the FIFO scheduling policy is based on. So if we forget about that, so let's cross it over and let's assume, let's move one step further. Let's instead assume that each and every job instead runs for different amount of time, right? Let's see how if FIFO is still working like efficiently. So here in this example, it shows the arrival timestamp and the CPU burst duration for the three processes, P1, P2, and P3, right? So as you can see, all of these three processes, they arrive at the system at exactly the same time, approximately 0, but they feature different runtime. And as you can see, P1 is the biggest job, which features the longest runtime, which is 80. And P2 or P3 are relatively short-lived. And both of them have a CPU runtime, CPU burst of 5 time units. So the question, also question number 3 in the CPU scheduling worksheet. So it's asking what's the average turnaround time for this example. Right, so the turnaround. So let's draw the Gantt chart for this particular example. So P1 arrived at the system at first. It featured extremely long CPU burst, which is 80, and followed by P2, followed by P3, both of which are relatively short-lived, and they finish, with only 5 time units. So the average turnaround time, so P1's turnaround time is 80, And P2's turnaround time is from the first timestamp time 0 to 85. And P3's turnaround time is basically 90. And the sum of these three divided by 3, right? Which gives you 255 divided by 3. So this much, right? Okay, so this is Gantt chart, as we've already seen. And average turnaround time is 85. Okay? So this is the so-called convoy effect, where we have one extremely long job, which blocks the way for the already arrived short jobs thereafter. And as you can see from this picture, this extremely slow-moving tractor blocks all the following vehicles. Okay, so in order to bypass the extremely slowly moving tractor, what we can do is we could effectively move those extremely short-lived processes, jobs, P2 and P3, ahead of this longest job, P1, right? As shown in this slide. So P2 gets scheduled first, followed by P3, and then P1, right? So this would, as you can see, this would significantly improve the average waiting time as well as average turnaround time, right? So, this motivates a new scheduling policy, as we've mentioned in our previous lecture, which is shortest job first, SJF. So its a core idea is pretty straightforward. When deciding which job to run, you just go ahead and choose the one with the smallest CPU burst time, the run time. Okay, but this is given the assumption that our operating system know exactly how long each and every process we're gonna run, right? And we're gonna, eventually cross over that assumption as well, which is obviously not realistic. Okay, so here this slide shows an example of shortest job first. Again, we use the same old example. 3 different processes, they are arriving in the system at exactly the same time, and P1 features extremely long time span, which is 80, and P2 and P3 features only 5 time units. So the question 4 in the working sheet is, what is average turnaround time with shortest job first? So you just draw the Gantt chart. So shortest job first. So let's assume it picks P2 first, and then followed by P3, and then we have the longest P1, right? So the turnaround time for P2 is 5, for P3 is 10, and for P1 is 10 plus 80 gives you 90, and the average turnaround time is aggregate all of these 3 factors and divide it by 3 gives you 105 divided by 3. Okay, so basically the next couple of slides shows the same calculation process. Okay, so as a result, you have 105 divided by 3 gives you, 35. As you can see, 35 is significantly shorter compared to the previous average turnaround time, which is 85. So as a result, a shortest job first is able to, effectively and significantly reduce average turnaround time, because it always, it uses a greedy algorithm, like a kind of heuristic, to always optimize for the average turnaround time and average waiting time, because it always picks the shortest job with the shortest CPU span, CPU burst. So let's revisit these 4 workload assumptions And at this time, let's cross over the first two. So instead of assuming all jobs are arriving at the system at exactly the same time, we kind of, relax the assumption. Instead, we assume all jobs arrive at the system at different point of time. Okay, let's see if the baseline shortest job first is still optimal in this sense. So in this example, this example is slightly different against the previous example. So if you take a look at the second column, the arrival timestamp. So the three processes, they have different time arrival timestamp. So P1 arrive the system at time 0, whereas P2 and P3 they arrive at the system at later time, which is time 15. Okay, so you asked to calculate the average turnaround time with shortest job first, which is the question number 5 of the worksheet. Well, even though your arrival timestamp is different, but essentially, if you use this non-preemptive shortest job first, which is a baseline case, we end up having this Gantt chart. P1 comes in first, followed by P3 and P2, right? So since P1, even though it's the longest, it arrived at the system earliest, so it effectively blocks the scheduling of P2 and P3, even though P2 and P3 feature the shortest CPU burst. But since they arrive slightly later as P1, so they get effectively blocked by P1. As a result, we get this average turnaround time. So we just sum these three turnaround time for the three different jobs together, which gives you around 83.3. As you can see, this is more or less the same as the average turnaround time if we go with FIFO. So within FIFO, we effectively achieve 85. So this is like essentially like FIFO, even though these two shortest jobs, their order is slightly different. Okay. So that's the inherent problem of the baseline shortest job first. So motivated by the observation, we introduce a preemptive version of shortest job first, right? So the new scheduler, which is called STCF, which is short of shortest time to completion first. So its policy is it's also used greedy algorithm, but whenever you have one job with a shorter CPU burst time, the operating system go ahead schedule that one and preempts the existing one which features relatively longer CPU burst duration. Okay. So again, let's take a look at the previous example. So this is the Gantt chart if we want to go with the baseline shortest job first, which is the non-preemptive version of shortest job first, right? It's more or less the same as FIFO, right, as you can see. But if we want to go with shortest time to completion first, the arrival of P3 will effectively preempt and interrupts execution of P1 at timestamp 15, as you can see from this Gantt chart. The operating system go ahead schedule P3. And since P3 finishes in 10 time units, the operating system go ahead schedule P2, which features the next shortest, CPU burst, which is 20, from 25 to 45. And right after done with P2, the operating system go ahead resume the execution of P1 so that P1 can finish, since P1 is the longest. So the question to ask here is, what is average turnaround time with shortest? Over here should be shortest time to completion first. Okay. So if you calculate the average turnaround time for P1, it is effectively 100 and 10, right? If you calculate the P2 average, the turnaround time for P2, so it arrived at the system at time 15, it gets finished at time 45. So its turnaround time is the span of 45 minus 15 gives you 30. And if you look at P3, its turnaround time is 25, subtracting 15, which is arrival timestamp, which gives you 10. You sum all these three together and divide the sum by 3 gives you the average turnaround time. Okay, so the next slide, it basically shows the exact value of the of average turnaround time, which is 50, which is a significant improvement against the previous baseline shortest job first, which is non-preemptive. Okay, so next question 7. What is average waiting time with shortest time to completion first? So how to calculate the waiting time? So if you take a look at P1's waiting time, so P1 gets preempted at time 15. It gets rescheduled back at time 45. So its waiting time is 0, since it first arrived at the system at 0. Its waiting time is 0 plus 45, subtracting 15 gives you 30. And if you take a look at P2's waiting time, P2 arrived at the system at 15. It gets scheduled at 25. So it's 25 minus 15 gives you 10. If you take a look at P3, upon P3's arrival, it gets instantly scheduled. So its waiting time is effectively 0. Okay, so these are the waiting time for all the three different processes. So the average waiting time is 30 plus 10 gives you 40 divided by 3. 40 divided by 3. Okay, so this is average waiting time for this particular example. So let's next. So that kind of finished the review session. So next we're gonna do a brief discussion about the optimality of shortest job first. So both the shortest job first, the baseline case, non-preemptive version of shortest job first, and also the preemptive version, the shortest time to completion first. So non-preemptive shortest job first is optimal, if all the processes are arriving at the system simultaneously at the same time, right? So recall that if the assumptions still hold true, if all the processes, the second assumption still hold true, which is all the different processes arrive at the system at exactly the same time stamp, the non-preemptive version of shortest job first is optimal, is able to achieve the best turnaround time and the best average waiting time. Okay, if the average waiting time is the performance metric, right? So the question to ask over here is, what is the intuition behind the optimality of the preemptive version of shortest job first, which is shortest time to completion first? Well, since recall that we cross over the second assumption, right? And then introduce a preemptive version, which means the motivation of preemptive version of shortest job first is based on that a more realistic assumption, which is all the different processes may arrive at the system at different point of time. So the intuition is, of course, shortest time to completion first is optimal considering a more realistic scenario where all the different processes may be arriving at the system at different point of times. Okay. So the as you can see, shortest time to completion first is kind of serving as a superset where the non-preemptive version of shortest job first is just a subset of this superset of shortest time to completion first. It's just one subset which is based on the assumption that all the jobs arrive at the system at different point at exactly the same time. So if you want to consider this ellipse, which is shortest time to completion first, and out of which we have a small circle, and this small circle is the shortest job first, is the baseline. Okay? Just because, shortest time to completion first is based on a relaxed assumption. So, right here, what exactly the problem? The problem is, even though, shortest time to completion first is optimal, and it's based on the assumption, a more realistic assumption that all the processes might be arriving at different times. But what we really don't know, what the operating system really doesn't know, is how long a job would run, because we don't have the capability to exactly and accurately predict the future. We don't have like perfect future knowledge, because future hasn't really happened yet. So how to exactly solve this problem? How to make accurate prediction into the future? Okay, so this is answered in this next slide. So how to give an approximate estimate about the length or the duration of the next CPU burst. So even though we could not predict the future, but what we could do is we could effectively leverage and exploit the history data, right? So what we can do is we leverage the historical data, and we use the history to make prediction into the future, right? And this technique, one of the estimation technique is called exponential averaging, right? Which is to assign different weights to different data points of the history, and you assign relatively higher weight to the historical data points in the near history, and you exponentially reduce the weight when you go further along the history. Okay. So here the bottom half the bottom half of the slide gives you the algorithm, the equation how to exactly calculate the exponential averaging. Basically, we have a decay factor, and this decay factor is set to 0.5. Okay, so next we introduce a new performance metric, which is called response time. And the definition of response time is the timestamp of the very first run, the timestamp of the very first, the starting timestamp of the very first CPU burst, subtracting its arrival timestamp. So the intuition behind this is whenever this particular process first gets scheduled by the operating system, it is when the end user gets the response from the operating system. So if you take a look at this example shown in the bottom half of the slide, the shortest, assume we're using baseline shortest job first, and since all the three jobs arrive at the system at the same time, and all three jobs have exactly the same CPU burst, so it's the job A's response time is 0. Job B's response time is 5 because job B gets to run first at timestamp 5. And similarly, job C's response time is 10. So the average response time is, just kind of like the average waiting time. It's 0 plus 5 plus 10 divided by 3 gives you 5. Okay. So this is shortest job first average response time, which is extremely high, as you can see, right? So here, this slide shows the subtle difference between these three different performance metrics: average waiting time, turnaround time, and response time. In this example, we have three different processes. So P1. So assume P1 arrives at the system at time 0, and P2 and P3, they arrive slightly later, which is at time 15. Okay. And over here, P1 is waiting time. If the question asks, what is P1's waiting time? Well, P1's waiting time is the span from time 25 to 45, because this duration is what P1 is not running. So its waiting time is 45 minus 25 gives you 20. And if you want to take a look at P2's turnaround time, so according to the definition of turnaround time is the completion timestamp subtracting the arrival timestamp. So if you take a look at P2's completion timestamp is 45, and it arrives at the system at 15, right? So 45 minus 15 gives you 30. So P2's turnaround time is 30. So the next performance metric gets introduced is the response time, right? If you take a look at P3's response time, so according to its definition, response time is the very first time that it gets scheduled by the operating system minus its initial arrival timestamp, right? So as you can see, P3 initially, its first schedule timestamp is 25. So 25 minus its arrival timestamp, which is 15, gives you 10, right? Okay. So the next question is, what is P1's response time, right? Because P1 has two different segments. The first segment is over here, and the segment is over here. Recall that the response time, its definition is the very first timestamp gets scheduled by the operating system. Obviously, P1 gets initially scheduled because it's the very first process that arrives at the system. It arrives at the system at time 0. So P1's response time is effectively 0. Okay. So next, let's take a look at the round robin CPU scheduling policy, which is another commonly used scheduling policy in real-world systems. So let's take a look back at these 4 different assumptions. So over here, instead of assuming all jobs only use a CPU burst but not IO burst, let's cross over the third assumption as well. Instead, we should assume the jobs they feature more realistic workload runtime behaviors. Besides the CPU burst, they also feature like IO burst. So basically, it follows the CPU burst followed by IO burst kind of pattern, interleaved execution behavior. Okay. So we now try to extend the original assumption where we only have purely CPU burst, and now we try to extend the model to kind of incorporate the IO burst as well, right? So let's assume when the process first arrives at the system, it will start off with initial CPU burst. As long as it completes the very first CPU burst, it tries to perform its first IO. Maybe it's done with processing its initial data that gets assigned, gets read from the disk. And in order to start the second round of batch processing, it needs to go ahead and read some more data from the hard disk drive, which requires the first IO burst, and then the CPU burst followed by IO burst kind of pattern interleaved, so as to make meaningful progress for this process. Okay. So round robin is based on this assumption, right, where the process features both CPU burst and IO burst, and the operating system effectively divide the physical time into logical time quantum or time slice, and the operating system arrives one or multiple time quantums to different processes in a, turnaround in a round robin fashion. And the newly arriving processes are added to the end of the ready queue. And if there are n processes in the ready queue and the time quantum is q, then a round robin guarantees that no process should be waiting for more than n-1 times q these many time slots, time units. So if we're talking about performance of round robin, if we have large enough time quantum, which is q, so this round robin effectively resembles the behavior of a FIFO policy. But on the other hand, with small enough time quantum q, this effectively achieves the so-called time sharing, processor-based time sharing, right? Because different processes, they take turn to use just a proportional share of the CPU processor. And, this is how exactly the operating system achieves CPU virtualization across multiple different processes. And it creates an illusion as if the system appears to the user, as if each of these n processes has its own a virtual CPU processor and running at the, the 1 divided by nth of the speed of the real processor. Okay, so it effectively achieves so-called CPU multiplexing or CPU virtualization. So this slide shows an example when the CPU, when the operating system is not IO aware. So in this example, we have two different processes, process A and process B. If the operating system is not IO aware, not IO optimized, so even though a process A is IO intensive because it features like CPU burst followed by IO burst, and whenever there is IO burst, the CPU becomes idle, right? Because the operating system is not IO aware, even though process B is CPU intensive, it's not able to effectively overlap the computation phase of process B with the IO phase of process A, which results in extremely poor use of the CPU resource, because for almost the first half of the CPU time, its CPU utilization is effectively 50%, but instead of 100%. Okay, so in order to further optimize this situation, we could make this operating system so-called IO aware, which makes operating system effectively support this so-called computation IO overlapping. In this, as shown in this example, a process A features a CPU burst followed by IO burst. Whenever it gets down to reading the data from the hard disk drive, the operating system will just go ahead and schedule another process, which is process B, which is CPU intensive process, to effectively use the CPU time quantums, which would have otherwise been wasted, which definitely allows for better utilization of the CPU resources, right? So in this slide, it shows the difference between these two CPU scheduling policies, shortest job first and round robin. So at the top half of the slide, it shows the average response time of shortest job first. Or you could kind of, understand this situation as another form of FIFO, because all the CPU bursts of these three different jobs, A, B, and C, they have exactly the same CPU burst. So they essentially resembles a FIFO, first in, first out. So if you want to calculate the average response time for this case, it's so since A gets started at time 0, B gets started at time 5, and C
initially first get started on time 10. So the average response time is 0 plus 5 plus 10 divided by 3 gives you 5. So this is the shortest job first average response time metric. If you take a look at round robin's average response time, if you take a look at the bottom half of the slide, assume we have a time quantum of 1, right? Which means we logically divide the physical time at the fine granularity of 1 time unit. And then, according to the definition of response time, it is the very first starting timestamp subtracting its arrival timestamp. So if you take a look at this example, process A, it starts at 0. So it has a response time of 0. And process B, right after it, because they take turns to run, right? ABC follow exactly the same pattern. So process B, its starting timestamp is 1, right? And then process C, its starting timestamp is 2. So this, as you can see, this dramatically improves the average response time. And the concrete result is 0 plus 1 plus 2 divided by 3 gives you 1, right? So this is the response time as a metric. If, on the other hand, you want to calculate the average turnaround time for these two different cases, these are all different. So, shortest job first at the top half of the slide, the average response time, it is A's response time is 5, and B's response time is 10, and then C's response time is 15. Divide by 3 gives you, so this is turnaround, 30 divided by 3 gives you 10. Okay, and in the case, for the case of round robin, the average turnaround time in this case is, so process A finishes in time for 13, right? And process B finish time 14. So it would be 13 plus 14 plus 15 divided by 3, 27, 42 divided by 3 gives you 14, right? So as you can see, if we use turnaround time as a performance metric, round robin is not necessarily good. It's only optimized for achieving a good level of average response time. It's good at optimizing in other words, the interactive user experience. Okay, so next let's briefly discuss about the trade-off consideration between shortest job first as well as round robin. So typically, round robin achieves higher average turnaround time as compared to shortest job first, but it definitely is able to effectively optimize for better response time as a metric. The intuition behind this, the rationale, is, the turnaround time only cares about when the process gets finished, whereas the average response time only cares about when the process first starting getting the CPU resources to start execution. Okay. On the other hand, round robin is considered one of the worst policies, if only if the turnaround time is a metric. So it's not good at optimizing turnaround time. It's only good at optimizing, the interactive user experience. In other words, the response time. Okay, as you can see, these two different scheduling policies, they exhibit this interesting trade-off. And whenever you want to pick a specific policy to use in your application scenario, and you need to pay special attention to these, what exactly the application cares about the most, right? So if the application is, let's say, interactive, like web application, which is required to feature low latency serving time, then round robin is probably better compared to shortest job first. So this is just a simple example in the real world cases. So next, let's talk about how to choose a specific time quantum to configure a round robin scheduling policies. As we've already seen, the effect of a quantum size, it leads to different levels of context switching activities. If you take a look at the graph at the bottom half of the slide, it shows 3 different examples, like with different quantum size. So the very first example, it shows the biggest quantum size, which is 12. As a result, it leads to a zero context switch activity, right? If we reduce this quantum size, the granularity of the quantum size, to half of it, from 12 to 6, as a result, we can see at least one context switch during the first 10 time units, right? But if we further reduce, like increase its reduce its granularity and increase its the frequencies of a switching time quantum, we would see dramatically increased total number of context switches if we use a time quantum, a final grain time quantum of 1. And this directly leads to excessive, like quite a lot of context switch activities, which is a total number of 9, right? So this would inevitably leads to a lot of, results in a lot of runtime overhead, because each and every context switch operation is costly. It involves saving the states for the currently running process and putting it back into a sleep and restoring the states, context states for the next available, next ready process. So it involves these 2 different subphases. It's kind of like a 2-phase protocol, right? So another observation is the turnaround time also kind of depends on the configuration, the size of the time quantum, as we'll see in the next slide. So in this slide, we shows a plot. It's a 2D plot, and the x dimension is the configured time quantum, ranging from 1 all the way to 7. And the y dimension is the performance in terms of average turnaround time, right? Obviously, the lower the better. As you can see, as we increase the time quantum, so in this example, we have a total number of 4 different processes as shown in the right upper corner of this graph. And these 4 different processes, they feature different CPU bursts, different runtime, right? And we want to use round robin to schedule these 4 processes. As we increase the time quantum, as you can see from this plot, there's no kind of predictable trend. As it shows, this trend kind of shows a zigzag behavior, kind of fluctuating up and down, right? So initially, it's starting off with an average turnaround time of 11. As you increase, it drops a little bit below 11 if the configuration of the time quantum is 3. And it spikes and skyrocketing all the way to 12 as the time quantum becomes 5, right? And all of a sudden, it drops to the very bottom, which 10.5, as we configure a relatively larger time quantum value, which is 6 and 7. And for both the time quantum values of 6 and 7, as we can see, for this particular problem size, it is able to achieve the optimal average turnaround time, but not necessarily means that the higher the time quantum is, the lower the average average turnaround time is. It doesn't have this, a linear relationship. Actually, it's fluctuating. Okay. So basically, this is a major takeaway, right? So you cannot just necessarily and easily predict the performance. For example, the larger the quantum is, the smaller the average turnaround time is. But you have to really carry out perform experiments to get the empirically measured results. Okay. But as shown, also another takeaway of this plot is, for the biggest time quantum value, it turns out to achieve like optimal turnaround time. So these are the several major takeaways we could get from the previous 2D plot. So let's revisit these 4 different workload assumptions. So in this case, let's cross over the 4th unrealistic assumption. So instead of assuming the runtime of each job is known ahead of time, well, let's assume more realistically, the runtime of each job is unknown ahead of time, right? So we don't know, which is more, practical and realistic assumption. We don't know ahead of time the runtime that each job will take. So let's next introduce priority-based scheduling, which is based on all of the, 4 more realistic, so the opposite side of those 4 previous assumptions. So priority scheduling, where the operating system needs to assign a different priority value, often in forms of an integer, to each process involved in the system. And the CPU is allocated to the process. With the operating system tends to assign CPUs more often to the processes with the highest priority. So how to define priority level? Well, we could use the integer value. A smaller integer value tends to mean, a higher priority. And priority just kind of like shortest job first. It could be divided into these 2 subcategories. One is a preemptive version of priority-based. The other is non-preemptive version of priority-based scheduling. Okay. So here in this example, it shows a total number of 5 different processes, and these 5 different processes, they feature different CPU burst time, and more importantly, all of these 5, each one of them has a different priority value, which is shown in the 3rd column of this table. And if you want to draw the priority-based scheduling Gantt chart, the bottom half of the slide shows a Gantt chart. So assume the lower priority value, integer value, means high priority. Okay, so in this case, a P2 with a priority value of 1 means the highest priority process. So the operating system would go ahead and schedule P2 first, and then go ahead and schedule the next priority level, which in this case is P5, and then followed by P1, which features a priority value of 3, and then followed by P3 and P4. So as a result, every waiting time in this case is the sum of all the waiting time of all the 5 different processes divided by 5. As a result, the every waiting time is 8.2. Okay, which is pretty straightforward, right? To continue, in order to assign priority values, the operating system or the system administrator, they need to consider a lot of both internal factors as well as external factors. So some internal factors including, for example, the timing constraint, the memory the resource usage requirements, and the ratio of the every diode burst versus every CPU burst. In other words, whether this process is, more CPU intensive or more IO intensive. So these are the internal constraints, internal factors. There are some other external factors as well. For example, whether this process is deemed as very important or less important, whether it has some financial consideration, and how would the user evaluate the importance of different processes. So these are all often considered as external factors, right? Which are kind of decided by the end users or the system admins. So with priority-based scheduling, there is this problem which is called starvation, that we've already discussed the definition. We've already seen the definition of starvation in our previous lecture, right? So starvation means some processes would just simply wait there indefinitely without getting the required CPU and memory resources to make progress. So in priority-based scheduling, in some cases, some processes with relatively lower priority, they suffer this indefinite blocking situation because, some other more aggressive processes with higher or highest priority, they tend to occupy and hog the whole system and inevitably starve those low priority processes. So in order to solve this starving problem, one commonly used technique is called aging. So what does aging exactly do? Well, so as time just progresses, the operating system will just periodically increase, check the priorities of all the processes and also check its waiting time of all the different processes. An operating system, with a simple heuristic, tends to increase the priority of the processes that wait in the system for the longest time. So this way, those relatively getting starved processes could just get a chance to run. Okay, and this solution is called aging, which is used to, tackle with the starvation issue that is commonly seen in priority-based scheduling situation. So next, let's talk about multi-level feedback queue, MLFQ, scheduling policies. So first of all, the ultimate goal of multi-level feedback queue is try to comprehensively combine the best of both worlds of shortest job first and round robin. So why is that? Because you may have recall in the previous slides, we've talked about the trade-off considerations of shortest job first and round robin, right? So shortest job first, if it knows about the future, if it knows about how long exactly each and every different process run, then shortest job first is the optimal policy when the average turnaround time or average waiting time is the major performance metric, right? But on the other hand, a shortest job first does not, naturally improve average response time, where round robin is one of the most effective scheduling policies for optimizing average response time. So here we are essentially looking at this two-dimensional scatter, two-dimensional opportunity space, right? So where we have turnaround time, so this is X dimension, and the Y dimension is the, let's say, response time. So the shortest job first. So the lower the better, right? So shortest job first. Let's use this red color to represent shortest job first. Shortest job first achieve relatively lower turnaround time, optimal turnaround time, but relatively higher response time. So let's say shortest job first is this red dots over here. Okay. And then we have round robin. Round robin is optimal for response time, but it's not necessarily effective for optimizing turnaround time. So as a result, we have round robin over here. So as you can see, these two different scheduling policies, they represent like two extreme points in this spectrum of two-dimensional performance trade-off space. Okay, and the ultimate goal of multi-level feedback queue is try to comprehensively combine, best of the both worlds and try to come up with a more comprehensive heuristic, more comprehensive mechanism that is able to optimize both the average turnaround time as well as average response time, right? So we have this green colored circle, and this is the ultimate objective of multi-level feedback queue. Okay, so it tries to perform some sort of multi-objective optimization and tries to optimize these two different sometimes contradictory objectives together at the same time, which are the average turnaround time and the average response time. Okay, so some basics about multi-level feedback queue. So first of all, multi-level feedback queue, as its name suggests, it maintains multiple different queues. So that is why it's called multi-level queue. So each queue gets assigned with a unique priority level, and often the topmost queue tends to have the highest priority, and the bottom queue tends to have the lowest priority. And the priority decides which process should run at a given point of time. Okay, so this slide shows a typical example of an AQ version of multi-level feedback queue policy. In this example, it has a total number of 8 queues, and the topmost queue is Q8, and the bottom queue is Q1. So Q8, whatever processes attached to the topmost queue have the highest priority, and as you traverse down, climb downwards the hierarchy, the queue hierarchy, the process tend to have like lower and lower priority. And the question here is how to know the process type in order to set priority. Well, so in practice, for example, in Linux operating system tends to assign a nice value to each and every involved processes at runtime, right? And the nice value, just as its name suggests, shows how nice this particular process is to other processes. So a higher nice value means this process tends to be like more friendly towards other processes, which also means it tends to have lower priority when in terms of getting CPUs and making progress. Okay, and this is the first metric to where the operating system leverage to set priorities to different processes. And the second metric is historical data, right? So just like the aging solution that we've mentioned in the previous slides, if a process tends to suffer starvation the most, maybe the operating system will just adaptively and periodically reboost its priority level so that it just eventually gets some chance to make progress. Otherwise, it just gets starved indefinitely by those more aggressive, processes with higher priority, right? So, how to check the nice value in Linux? Well, you could use this following command. You use this ps command 2, which is used to list all the running processes within operating system, and you pass in these two options, AX, right? And then followed by flag -O, and followed by the format PID nice value, and this is a nice value, and also command, right? This is how exactly check the nice value. So again, looking back at this example, in this particular example, process A and B are given the highest priority to run because they initially get attached to the highest priority queue, which is Q8. Whereas process C and D tends to have lower priority. But in this case, process C gets relatively higher priority compared to process D because process D is attached with the lowest priority queue, which is Q1. Okay. So now here next, let's introduce the various different rules used by a typical multi-level feedback queue, right? So here we introduce the first two basic rules. Rule 1, let's assume we have two different processes, process A and process B. If process A, it has a priority, its attached priority is larger than that of process B, then A would run while B doesn't, right? So this is the very first basic rule, which is quite easy to understand. And then rule number 2 is, so what if the priority of process A is exactly the same as that of process B? And the operating system decides both process A and process B, they take turns to run. Basically, they follow the round robin policy. Okay, so these are the two basic rules of a multi-level feedback queue. So the over here, the next slide, at least the workload of different policies that we're gonna walk you through the next couple of slides. So the workload, it features these two different kinds of processes. So we have this relatively interactive process, which is relatively features relatively short-lived CPU burst, but maybe it has like I/O burst, but we don't know yet. But essentially, it's interactive process, which is not CPU intensive, and this is the very first type of process. And the second type of process, which features dramatically different workload behavior, is this long-running process, which are obviously CPU bound. They just tend to make full use of the CPU resources because they are CPU intensive. For example, matrix multiply, deep learning, whatever, right? So these two different processes, they exhibit dramatically different performance and resource requirements. And assume we configure the duration, the size of each time quantum to be 10 milliseconds. Okay, so this is a workload specification, the workload characteristic. And at the bottom of the slide, we further introduce another, two different policies, two different rules. Rule number 3, when a job enters the system first, it will be placed at the highest priority, which is the topmost queue. So that means whenever a job initially first arrives at the system, it gets assigned the highest priority to run. So this is rule number 3. And then rule number 4. So this rule number 4 gets further divided into two sub-rules. Rule 4a means if a job unfortunately uses up an entire time slice or time quantum while running at the relatively higher priority queue, its priority gets reduced, which also means it gets demoted, right? It gets demoted, downgraded from the top level queue to the next level, which means its priority gets reduced. So this is the first sub-rule under rule number 4. And the second sub-rule under rule 4 is, rule 4b. If a job, it gives up the CPU before its allotted time slice is used up, it would stay at the same priority level. An operating system won't drag it downwards to the next level, which tends to have lower priority. So this is the second sub-rule under rule number 4. Okay, so keep the second set of rules in mind, because in the next couple of slides we will, revisit these several different rules, see how these rules are encountered and applied in the workload. So here in the first example, let's assume we have so the whole system has only one single long running process, which is CPU intensive. So again, recall that the time quantum is configured to be 10 milliseconds. So according to, rule number 1, right? When a process initially enters the system, it gets placed to the topmost queue, which has the highest priority. So in this example, assume we configure multi-level feedback queue, which consists of 3 queues: Q2, Q1, and Q0. And Q2 features the highest priority, whereas Q0 features the lowest priority. Okay, so after this long running process use up its allotted time quantum, it gets demoted to the next level. So recall that this is rule 4A, right? It gets demoted from this level to the next level. And then, again, we apply rule 4A over here. So it further gets demoted from Q1 to Q0 because it fully used the time slice allocated when this process is running at level of Q1. So given that Q0 is the bottom level, so there's no further downgrading, it will just end up running at the lowest level, Okay. So this is the first example. What if there's only one single long running process? And in the second example, alongside this long running CPU intensive process, let's assume we have at some time, in the middle of some time, we have a company, a short running interactive process, okay? So initially, starting off, process A has already fully downgraded to the bottom queue, which is Q0, okay? So it just keep executing until time 100. And then at time 100, a short running interactive process kicks in, right? So this will make the operating system preempt the execution of process A and let go for process B, because process B, according to rule number 1, for whenever process first arrive at the system, it gets placed to the topmost priority queue. So that is why we have process B over here. And next, so as long as it uses up the first allotted CPU slot, which is 10 milliseconds, it gets downgraded to the second level. But since the second level is Q1, which is still featuring higher priority compared to Q0, so it's still process B's turn to run. So okay, until it finishes its second time quantum, which is another 10 milliseconds. And after its second time quantum, it gets finished because it's relatively short-lived and IO intensive, right? So maybe its current CPU burst just gets finished, and its next IO burst is going to be starting. Okay, so then it gets finished and leave the system, and then rest of the time it's a turn of process A to run, right? The control gets back to process A, but process A still stays at the lowest level, which is pretty natural for a typically CPU intensive process, which is process A. Okay, so this is the second example. So we have a relatively long-running CPU-intensive process together with a company of relatively short-lived interactive process, which is process B. So this is how multi-level feedback queue handles these two different processes. And then further, we have the third example. How about we incorporate IO bursts? We take IO bursts into account, right? So again, in this example, we have these two different processes. Process A, long-running CPU-intensive process, and then we have process B, the IO-intensive interactive process where each CPU burst is only 1 millisecond. Okay, so these are all 1 millisecond. 1 millisecond. Okay, so this is obviously IO intensive. Right, as you can see, according to a rule 4B, right? So what's content? What does rule 4B specify? It specifies that if a process gives up its usage on its allotted CPU time quantum, the operating system would still allow this process to stay at exactly the same priority level. So this is what exactly this process B, IO-intensive process B, is doing, because each and every of its CPU's burst is only 1 millisecond, which is dramatically shorter than the allotted 10 milliseconds time quantum. So the operating system would allow it to stay at the highest priority level, which is Q2. So as a result, these two different processes, they take turns to run, right? Now, first of all, process B burns like 1 millisecond CPU, and then followed by the CPU intensive process A, right? And after done with the process A's CPU burst, then the process B takes turns to run. So as we can see, we have this interleaved like small white space like in between a process A's runtime behavior. Okay, so this is essentially like round robin, but it's only different in the sense that these two different processes, they stay at two different priority levels. So this is how exactly this comprehensive version of this scheduling heuristic, namely multi-level feedback queue, is able to effectively combine, both round robin together with, priority-based kind of shortest job first. It's not essentially shortest job first, but it uses priority to kind of approximate the behavior of shortest job first policy. Okay. So in our fourth example, so this tends to be a more interesting situation. So again, we have our old friend process A, which is a long-running CPU intensive process, but it got an interesting company of a group of different processes, process B and C. So this process B and C, both of them, they are interactive processes, but it's different from the previous example in the sense that both process B and process C, they tend to be more or less like malicious, right? So they try to game the system in the sense that they take turns to run, but instead of using up the full CPU time slice, they only use half of it, for example, 5 milliseconds. So this gray colored rectangle, this box, they feature like 5 milliseconds, okay? So they take turns to run. And according to rule 4B, if you never use up its fully allocated time slice, the operating system would allow it to stay at the same priority level. As a result, it starves the CPU intensive process A, right? And the process A never gets a chance to run, as long as this malicious group of process B and C, they kicks in and arrive at the system at time 100. Okay? So how to resolve this situation? How to solve this problem? Well, a simple idea. It's kind of like aging, right? So just periodically boost the priority values for all the involved processes in the system. So as a result, we introduce the last rule, which is rule number 5, which is specified over here. So after some time period S, which is configurable, obviously, okay, and move all the jobs in the system to the topmost queue basically means boost the priority values for all the processes involved in the system, as shown in the bottom half of the slide. So initially, process A arrives at the system. It gets demoted to the next level and then to the bottom level, and then let's assume we configure S to be 50 milliseconds. It means every 50 milliseconds, the operating system reboosts the priority for all the processes. But during the first first half of the time, during the first 100 milliseconds, there's no other process, only process A. So basically just drag process A all the way up to the topmost queue, which is Q2, and then it gets downgraded to the bottom, and then reboost. Okay? And then after some time, this malicious, interesting group of process B and C, which, try to game the system, they arrive at the system, at time 100-ish, right? So they take turns to run. They cooperate with each other like really strategically and smartly. So they successfully fool the system and starve this poor guy, which is process A, right? So they use the rest of all the time slides during the third 50 millisecond. But because we have this periodic priority boost mechanism, after 150 milliseconds, the whole system gets reboosted, so that eventually process A gets some chance to run, at least gets allocated one more time slice, which is another 10 milliseconds to run, and then followed by the running of these two different processes, B plus C. Okay, so this is a simple technique, priority boost, to solve this starvation problem. So as we can see, since multi-level feedback queue is comprehensive, more real-world oriented CPU scheduling heuristic, it naturally features a lot of configuration knobs, configuration parameters, right? So for example, how do you decide how many number of queues to be used in your system, and how decide the time quantum for each and every different queue, because different queues could be configured to use different time quantum, and how frequently should the priority be boosted, and so on and so forth. A lot of different configuration knobs. So this definitely require a previous experience of running and using the system. It also is kind of determined by the external factors, external constraints, like what exact workloads are going to be running for this system, right? So if the workload characteristic, the workload behavior, runtime behavior, its resource requirements, its performance characteristic gets changed, maybe the system admin will need to think about changing the multi-level feedback queue, reconfiguring multi-level feedback queue to further accommodate this new change in the workload. Okay, so that completes the most important CPU scheduling policy, multi-level feedback queue. So next, let's take a look at another interesting scheduling policy, which is called lottery scheduling policy. So as its name suggests, lottery scheduling policy works kind of like our daily life lottery example, right? So different processes, they just draw lottery, they get assigned with random number of lottery tickets, and depending on how lucky they are, maybe in the next round they get picked by the operating system to use the CPU cycles to run, right? So the ultimate goal of lottery scheduling is to achieve proportional share of the CPU resources, proportional share of the CPU time, right? It's one of the fair share, so-called fair share CPU scheduler. Okay, depending on how many lottery tickets gets assigned to a different process, it gets its fair share of the CPU resources, okay? Statistically. And high priority means more tickets, obviously, okay? So this slide shows the pseudocode, the high-level pseudocode of the internal working mechanism of lottery scheduling policies. So let's just briefly walk through this, how exactly this piece of code works. Initially assign a counter, right? Initialize as 0, and then we get configured this total number of tickets, and then you just draw a random ticket from this all the tickets, right? and you pick a winner. This is just like a random number generation. Okay, get random, you get a winner, and then you enter this while loop. So during each iteration, you just provide this sum of the tickets value that you've already observed so far, which is the counter. You compare counter with the winner. If the counter turns out to be like bigger than the value of the winner, you just simply break out from this while loop, and then this current is a pointer, right? So whatever pointed by the current pointer is the winner, and the operating system go ahead assign the next CPU time slice to this current winner. Okay, so this is roughly how it works theoretically. So next, let's use this simple example to further illustrate how lottery scheduling works. In this simplified example, let's assume we have a total number of 402 tickets, lottery tickets. And in the system, assume we have a total number of 5 different processes: job A, job B, job C, D, and E. And as you can see, these 5 different jobs, they get assigned different number of tickets. So this total number of 402 tickets gets like unevenly distributed across these 5 different jobs. So job A and B, they tend to be, they're unlucky in the sense that each one of them, they get only one single ticket, which means their chance of getting the CPU quantum is extremely small. And the next job C, it gets assigned 100 ticket. It means its chances is high, but not as high as job D, which gets the highest number of tickets, which is 200. Okay, the same. A job E, it gets a fair share, another 100 share of the tickets. So starting off, let's say the lottery tickets scheduling policy starts iterating from job 1. Okay, so let's assume we just randomly draw a winner from all these 402 lottery tickets, and turns out the winner is 102. Okay, somewhere between job C and job D, and either one of these two might become the winner, it turns out, right, as it pans out. So initially, how the algorithm works is just iterate through all the 5 different processes and check the aggregated sum of the ticket that is seen so far is greater than this winner or not. It turns out for job A, 1 is obviously smaller than 102. So it just simply skip job A and directly move on to job B. And so far the sum of all the tickets is 1 plus 1 gives you 2, right? And 2 is obviously smaller than 102. So move on to the third process, job C. So far the sum is 100 times 2 gives you 102. 102 is, unfortunately the same as 102, but not necessarily larger than, right? So just skip process C and directly move to the fourth guy, which is job D. So job D has the biggest share, the largest share, which is 200. So accumulating all the total number of tickets that it's seen so far results in a bigger number, which is 302. Obviously, 302 is greater than 102. So it turns out the winner is process D, right? And then operating system will just go ahead, picks job D to use the next available CPU time quantum to execute. Okay, so this explains how, the lottery scheduling policy works internally. Okay, so that kind of, finishes the CPU scheduling topic. In our next lecture, we're going to start a new topic, which is virtual memory management. Okay, thank you.